It's been said, my name is Razin Igor. You can call me George if you like. As a mathematician, today I will tell you about the Banach Tarski paradox. Long story short, 1 equals 2. And to properly understand the statement, one should understand the proof of said statement. So you'll be taking step by step through the theorems required to adequately prove the paradox. First, you will learn about the countable infinity and its uses. Then we'll blow your mind with uncountable infinity. After that, we will rediscover all the tricks and properties of the uncountable infinity. And finally, we will neatly prove the paradox itself. Do you see the slides changing?
Not yet.
All right, I guess I'll have
you will have to show it like that, probably.
Yeah, show like that. Not good, not good. Anyways, let's continue. First and foremost, what the paradox states. Given a solid sphere in three-dimensional space, there exist decompositions of the sphere into a finite number of disjointed subsets, which can be put in a specific way, creating two identical copies of said sphere. And the preamble. To actually build up to the proof, let's introduce the concept of infinity and how to count both to it and past it. Countable infinity. For example, amount of years, months, or seconds in eternity. It's all countably infinite. Or a list of all natural numbers that we use to count stuff with. It's actually a definition of countable infinity. Surprisingly, amount of all even or odd numbers is the same. It's still countable infinity. Let's take a look at the famous Hilbert's Hotel. This hotel has infinite amount of rooms. Let's say all of them are taken. And at the same time, a new guest shows up at the reception asking for a free room. Some of you may think, wow, unlucky. Guess this little fella will have to sleep outside tonight. Nuh-uh, you'd be wrong. Remember, infinity does not know what a volume is. All the owner of the hotel has to do to free up one additional room is to tell every guest to shift one room up ahead. The amount of rooms hasn't changed, only the amount of guests, yet everyone has a room. Therefore, we just proved that infinity plus 1 is still infinity. Now let's get to the mind-blowing stuff. Uncountable infinity. There's no simple way to give an example in the real world, so let's just prove a little theorem for you to get a grasp on it. Amount of numbers between 0 and 1 is greater than the amount of all natural numbers. Yep, what was that?
Please turn off your microphones.
Anyways, let's ignore that.
Hello, is it Natalia Konstantinovna? Please turn off your mic.
Oh, okay.
Hey, fellas.
Sorry.
All right, thank you very much. Let's continue. Let's say I gave you infinite ink and paper, and I've gave you a task to write every number between 0 and 1 and assign every real number to it. You've covered every single one of them, so you think. That means you have no free natural numbers left in the bag. All of them are taken. All of them are assigned, as you did. So when you show me that list, I can take the first digit of the first number and change into whatever number. For clarity, let's make a rule. I subtract 1 if it's 9, and I add 1 if it's anything else. By doing that, the resulting number will be between 0 and 1, but most importantly, it will not be on the original list. And because all natural numbers are taken, and there is at least one real number, we conclude that the amount of numbers between 0 and 1 is greater than the amount of natural numbers. Then let's jump into the cluster dictionary. Say I want to create a dictionary that will contain all words made using English alphabet. And I mean all of the words. They don't even have to make any sense. It could be A, it could be chair, it could be BAA, it could be anything. All that matters is that we use the English alphabet. So let's split them into volumes. For example, all words starting with A will be in the volume 1, volume A. all words that start with J into the J volume, Z into the Z volume, and so on. Here's the thing. Since the letter that all words start with is in the number of the is in the name of the volume, we can simply not write that letter in front of that word because it's a name. It's supposed to be there. By doing that, we actually created 26 identical copies of the original infinite volume, original dictionary that contains all the possible words of English alphabet. Remember that trick. We can take something, split it into parts, and make copies of it. Let's look at the circle example. This is the last thing we need before moving on to the paradox. The statement is the amount of points on a circle is uncountable infinite, and therefore we can do a little trick. Circumference of a circle is 2 times radius times pi. Pi is irrational, meaning it cannot be presented as a result of dividing two numbers. So let's say that I stole 1 point from the circle, just because I felt like it, and now there's a gap. It's possible that we can go along the circumference a distance of a rational number and put a point we'll end on instead of a missing point that I took earlier. And since the circumference is rational, we'll never encounter the same point twice. And by setting these rules, we actually have the situation just like in the Hilbert Hotel example. We can just shift all the points by 1 and get rid of the gap. Uncountable infinity minus 1 is uncountable infinity. Now let's get to the paradox itself. So we have a sphere with uncountably many points on the surface, and let's identify each one of them in a very specific way. We can assign a unique sequence of moves from a unique starting point to each point on a sphere. If it ends with a move up, we call it the north point, move left, west, same applies to south and the east. And let's make one rule, which is allow direct backtracking. For example, if you move 3 times to the north and 1 time to the south, it's not a south move. It eliminates not north and south. They cancel each other out. So that will still be a north movement, not a south one. Now we have north, west, south, and east group of points. And we have the starting points themselves. We need to start from somewhere, right? And each starting point has actually 2 poles. Since it's possible to reach a pole in different ways, we can split them into a different group of points so that there will be no mix-ups. Now we split the sphere into 6 separate groups. This allows us to rotate the east group to the west, just like in the dictionary example. We modify a group slightly, and we get parts of the original copy. So we rotate, for example, the east group to the west. That duplicates the south, the north starting points in the east group itself. Then we can do the same for the north group, but there's a problem. By doing that, we actually now have 3 sets of starting points. So let's move 1 step back and say that in the north group, we only rotate those points to the south that do not result in a starting points group. Okay, we only need 2, not 3. As is shown on the slide, we do that. So now we have the original sphere and an additional sphere, but without poles and the starting points. Without the poles, sorry. Since all the missing points are on the surface of a sphere and therefore on the surface of a circle, that means we can fill the gaps by shifting points on that circle, just like I mentioned in the circle example. And by doing that, we now have 2 identical spheres just from one sphere. In conclusion, I'd like to state that the sphere we're talking about isn't a sphere in a normal sense. It's not a real sphere in a real world that you can touch, you can split it into 2, etc. It's a fractal-like structure because it's constructed using infinitely small points. This whole object is uncountable infinity in the shape of a sphere. And its property to be able to fill any volume is a reminder of that. So remember when I told you that in short, the paradox states that 1 equals 2? Well, that was a bit misleading. More accurately, it can be summarized as infinitely equals infinity plus infinity. Thank you for listening to my TED Talk.